Okay, so welcome back, and now we're going to talk about elimination. So we're going to take a break from substitution because that's what we've been doing with these alcohol reactions. We've been adding something onto an alcohol, getting rid of the alcohol group, and replacing it with something else. By definition, that's substitution. But now we're going to take a look at elimination. That means that when we have an alkyl group that's attached to an OH, we can target this OH group and whoop, completely eliminated. It goes away. Nothing goes on in its place. Nothing. We don't bring in a prettier group. This carbon has made the decision to be single for a little bit. Maybe you've been that point in your life at some point in time. I don't need somebody else. I can take care of myself. And away you go. Well, sometimes carbons are that way too. So we eliminate the OH group. Carbon does not need another person to be involved with in a relationship. And that OH group gets eliminated. And when that does, carbon still has to have 4 bonds. So typically what we end up here with, when we saw eliminations before in Chemistry 251, is an alkene. That is a carbon double bond carbon. So an alcohol group can undergo an elimination reaction. It eliminates OH. A neighboring, though, atom has to have a hydrogen that it can get rid of, and that is what allows the double bond to be formed. This OH and H come together, and that makes water, which is why very often these elimination reactions for alcohols, they are called dehydration reactions. Dehydrate? What does that mean? Dehydro, removal of water. Dehydration. Now, these elimination reactions are always going to require something special, and this is a pretty strong acid. It's an acid catalyst. Now, by definition, it's not a strong acid. There's only 7 of them. One of them typically is thrown into that group, even though it has multiple protons that it can give off, and that's sulfuric acid, H2SO4, and the other one is going to be phosphoric acid, which is H3PO4. So these are the 2 acids that we typically deal with when it concerns dehydration. Well, why not HCl? Hello. We don't use HCl because we've talked about HCl protonating the alcohol group, bam, giving it a black eye, making it leave, and replacing it with chlorine. Well, why not HBr? Hello, we talked about that too. All of the hydrogen halides, those hydrochlorics, hydrobromics, hydroiotics, we do not use because those promote substitution, not dehydration. But there's a couple of acids, sulfuric and phosphoric, that do promote the elimination of an alcohol. And these are the ones that we use. Again, very cheap. A lab typically has them almost every single time. I can take a pretty cheap alcohol. I can take a pretty cheap acid. We can go to Taco Bell and have a cheap, easy date, and then all of a sudden I get an alkene. And these alkenes, if I have to order them on my own, folks, we're talking hundreds of dollars for a bottle possibly. So why not make it in a lab if we have the available ingredients to make it with? No big deal. The dehydration of secondary and tertiary alcohols, this is going to undergo an E1 mechanism. Again, there's 2 different types of eliminations. There's E1 and E2. If you need that review, go back, review those elimination folders that I've made available for you. Again, no assignments are there. Put me on double speed. You're probably watching me at double speed right now, and if so, that's okay. I would too if I was you. And that will give you a review of substitution and elimination. Now, Let's talk about the mechanism. Let's talk about the mechanism. Let's talk about the overall reaction that goes on. And this is what happens. Let's say I give you an alcohol. CH3, CH, CH3 with an OH group here. Isopropyl alcohol. That's rubbing alcohol. And then let's bring in an acid. Let's just say this is H2SO4 with some heat. What goes on? Let's talk about that first. What happens? Well, you know me. I'm going to always start off with my reagent, CH3, CH, CH3 with an OH that's here. And an elimination will go on, which means this acid targets that OH group. Whoop! It goes away. And when it goes away, nothing goes on in its place. Hello, it's called elimination, not substitution. So in order for this to complete, this carbon is now going to look to the left and to the right, and it's going to say, okay, I'm short a bond, and I need a fourth one. I'm not going to be able to make this fourth one. I'm going to have your help. You're my buddy. Hello, you're going to have to bail me out. I just got arrested on Friday, Saturday night downtown Wilmington because I was acting stupid at a bar. That's what that carbon's telling its friends. And the one to the left and one to the right, they're pretty much the same, right? CH3 to the left, CH3 to the right. No big deal. It doesn't really care which one it comes from, as long as it gets something from someone. And I'm going to put over here to the left-hand side. This carbon's going to say, okay, I got your back. I'll be there in 15 minutes. So this carbon has to give up something in order to make that carbon happy. They're friends. They look out for each other. And it's going to give up a hydrogen. So that turns into a CH2. So now this carbon has a spot available, maybe a bedroom. This carbon has a spot available. It's just been kicked out. It's got nowhere to go. And this buddy goes over to that buddy's house and crashes for the night. They've got the available space to do that now. So a double bond gets formed in between them because they talk crap all night long about what happened. They laugh about it. They have some drinks. They go to bed. They pass out. They wake up the next morning, and there you go. So that is an elimination reaction at its heart. That's what goes on with the sulfurics and phosphoric reactions with alcohol groups. Now, this was a pretty simple kind of molecule, right? I mean, when the OH was removed, there wasn't too many choices, was there? I mean, the choice that we had was the same, left-handed or right-handed. That's good, though. That's how we like to start out. Let's do another example, this time with a ring, just to show you that rings really are no different. So there's the ring with an OH group. That's cyclohexanol. And cyclohexanol could react with phosphoric acid. Let's say H3PO4. It's one of those acids that I could choose from. Either one's okay. And let's look at the overall thing that takes place. So I'll start with my reagent. There we are. Here's where the OH group was. I'll draw that again. And an elimination reaction will happen. Which means, just like before, bam! OH goes away, gets ripped off, away it goes. So this carbon just got arrested. That carbon needs some bail money from a buddy. And it looks to the one on the left toward the top. And it looks down to the one toward the bottom on the right. And it says, hey, you got to help me out here. What are you going to do? I need something. Either one of these carbons, it doesn't really matter. They're both the same. CH2, CH2. And I'm just going to do the one up at the top. So that carbon has a hydrogen that gets removed. It opens up an available room. That carbon moves in for the night, maybe long term, who knows, and a double bond forms. So in the top one, isopropyl alcohol. The IUPAC name for this, 1, 2, 3 carbons. That's a propane, drop the E, add OL, 2-propanol. Has made 1, 2, 3. This is a propene. And I can put a 1 in front to represent that's the double bond location. 1-propene. Down here below, this is cyclohexanol, because of the cyclohexane ring. I can put a 1 there if I want. It's understood to be there. I don't need it. And cyclohexanol has reacted with phosphoric acid in the presence of heat to make cyclohexene, because that is a double bond, and that double bond is an alkene. So overall, folks, this is the take-home message. You add the acids, OH gets ripped off, a neighboring hydrogen will get ripped off, and we form a double bond in the mix. All right, so this, again, meat and potato kind of stuff that you need to take home with you. Now, let's talk about mechanism for a minute. You know, again, sometimes it's very important for us to understand how this works. So CH3, my CH, and CH3 with an OH group. All right, so there was the first alcohol that we used in our first example. Now, in the first example, we did sulfuric acid, H2SO4. So I'm going to draw this a little differently. So there is the first H of H2SO4. And SO4, I'm going to rewrite. That looks kind of like this. All right. Why am I doing that? I'm looking at actual structures. How are they linked up? You're going to see that this is how they're linked up pretty much. So I'm just putting maybe a priority on one of those hydrogens out of the bunch. That's what we're doing, because that hydrogen is going to be very important. So mechanism of the elimination reaction. That's what we're dabbling into now. Now that we have an overall picture of what goes on, how does it actually happen? Well, the oxygen here is negative. I see the dots. It wants and wants and wants and wants. And that oxygen is going to be attracted to this positive hydrogen because that oxygen is an electron sucker as well. That's a partial positive hydrogen right there. So this OH group says, hey, hydrogen, why don't you come with me? Just get out of that relationship with that O and the S and the O3s and the H. There's too much going on. They've got nothing to give you. Why don't you come over with me? So that hydrogen says, okay, and it does. So when that hydrogen leaves, these electrons are going to now be pulled into that remaining sulfuric acid molecule. That oxygen's electronegative. It's electron greedy. It wants them anyway. Okay, so when this first step of the mechanism happens, what we have left over is a CH3, a CH, a CH3, with now an OH, but an extra hydrogen that's down here too. That OH group just pulled that one off. It's got to go somewhere. It attaches. But now that oxygen realizes that maybe it made a mistake. Okay? It has too many bonds. We see oxygen do this all the time. It doesn't think ahead. It has too many bonds at this point, and it's got to get rid of them. So at this point, this oxygen turns into a very good leaving group, doesn't it? Very similar to what we saw on the substitution kind of side of the house with the early alcohol reactions. So this part of the mechanism, that oxygen-containing group leaves in form of a water molecule. H2O goes off. Okay, this allows a carbocation to be formed. Now, I'm going to do something in the next step of the mechanism that's a little strange, but again, it's important that I do it this way because I'm getting ready to place a focus on one of those hydrogens. Remember, I told you a buddy's going to have to come in and save the day. A buddy's going to have to get rid of something in order to make room for this extra carbon and its needs. So that carbon donates a hydrogen. That's what we said before, and I need to show that in the mechanism. So this CH3 group that's over here to the left, I'm just going to rewrite it a little bit. I'm going to do CH2 with a hydrogen that's pointed up. So here we have a CH and a CH3. Now this CH is a carbocation at this point. We have just popped off a water molecule, haven't we? There we go. There's my water molecule. Whee! Away it goes. But that water molecule is still around. That water molecule can still associate itself with one of these alkene structures. That water molecule is negative. I see that negative oxygen with those free pairs. And we have a neighboring carbon that could donate a hydrogen. Somewhat basic or acidic. So here this nucleophile can come in, let me switch my pen to red, and attack that hydrogen and rip it off. Well, it's only going to rip the hydrogen off. These electrons now move back into the molecule because those electrons are negative, and it sees that carbocation, and folks, they move toward each other. Opposites attract. And this is the formation of my double bond that happens between those first two carbons. That's where those electrons are coming from. The electrons have to come from somewhere, and they're coming from the electrons that were involved in the bond to one of those hydrogens before it was ripped away. Now let's talk about this water molecule. This water molecule, when it grabs the hydrogen and pop, off it goes. This now is going to form H3O. And this H3O is an acid. And look up here. It regenerates the acid all over again. So we get these acidic conditions that happen at the end of this process. You know, we put the alcohol into a flask. We add sulfuric acid in the beginning. We allow these things to react with each other, and they do. And in the process, we're generating acid yet again at the end result. So we have this alkene, and then we also have acid, like H2SO4, that's getting regenerated, and we're also getting water as well. Now, here's the problem. Look at this. It's generating acid and water. Oh, gosh. Acid, water, and an alkene. Let's think about Chemistry 251. This was an alkene reaction. That means if I don't do anything here, this alkene's going to form, but my water and acid's going to form as well. And water and acid is just going to turn around and break the double bond, and two sides of attachment open up here and here. Hydrogen plays on one side and oxygen with the H plays on the other. I regenerate the alcohol. It's a losing battle. I can't have that. So very often it is important to do something like distill my product off as it's getting generated. If I do not do that, my alkene that I'm forming down here in the very bottom is just going to revert back to the alcohol because the byproducts here are water and acid. And that is the template that's needed in order to make an alcohol from an alkene. We're working backward. It's going to go backward if I'm not careful. So very often in these procedures, you might see a distillation process as the reaction is going on. The reason is that these alkenes typically have low boiling points, and those are lower boiling points than something like water or something like acid. But I will be able to separate these in some form or some fashion. I can do the second one the same way if we want to draw that mechanism. Not a big deal. We did this ring structure, and this ring structure we had H3PO4. So I'm just going to draw one hydrogen that kind of sticks out. And just to make this simpler, I'm going to put H2PO4 here. just so I don't confuse you. It's not really important. We're just putting a highlight on the hydrogen. So this oxygen's got some free sets of electrons. There they go. We always see them. The first step of the mechanism, that oxygen negative is attracted to that partial positive hydrogen, and that shoves the electrons to the H2PO4 group. When that happens, I get a ring structure. That ring structure now has this OH with an extra H on it and a positive charge. The oxygen does not like that. It's got too many bonds now. It forms a very good leaving group, and it leaves. So it takes those electrons and whoop, away it goes. So now, in the next step of the mechanism, just like before, we have my structure and a full-blown carbocation that's now formed. That carbon needs help. It looks to the buddies. And with the acid content that we have, this acid content is going to look at that molecule and say, neighbor buddies, you got to give me something. You got to give me a hydrogen. All right, so we tackled the one up at the top. So I'm going to draw the hydrogen kind of out like this. It's not drawn. It's understood to be there. So that water molecule that just left is still lingering. It's like one of those crazy exes, right? I mean, they're always at your house. They're always calling. They're always sending you emails or text messages. You can never get away from them. That's what this OH group is going to be, this water molecule. So in this step, this water comes in and says, and it takes that hydrogen and it removes it. That leaves the electrons here. Those electrons get shoved down into the ring, and that is what forms the double bond that we drew there in that product. Again, this is how it actually happens. That's the purpose of the mechanism. Way complicated than just looking at a reagent and saying this is what's going to be made. But folks, this is why these steps are happening. That's why we look at them, right? We got to have proof in the pudding. And here's our proof. Now, we're eliminating. Something else that we want to review with elimination, which are the easiest. Well, tertiaries are going to be easier than secondaries, which are going to be easier than primaries. And within this category, you also want to look for delocalization, which means that if you get a secondary that could delocalize and a secondary that could not delocalize, the delocalization is going to be preferred. The same way with tertiary. If you have a tertiary and a tertiary delocalized, the tertiary delocalized is going to be preferred over just the straightforward tertiary version. But these are the easiest in order to eliminate as far as these reactions are concerned. You're also going to have choices. We started off very simple. So what did that mean? What does that mean? Let me give you another example. CH3, carbon, CH2, CH3. Here is my OH, and here's the CH3 that's hanging up. I'm going to react this with sulfuric acid. It also requires a little bit of heat. Another key thing that I've not mentioned yet, see that triangle? This is heat. Back in the world of substitution and elimination, heat drove elimination reactions. That's a very good thing because that's what we're doing here. We're eliminating. So that heat is a very good thing for this reaction. It promotes elimination, which is the removal and the staying away of the OH group as we remove it. Just a little tidbit of information there. Okay, so what happens here? Okay, we've got a couple of choices. I'm going to write down both choices. Here's my CH3, my carbon, my CH3, the OH group, and then my CH2 and my CH3. And then there is another choice, so I'm going to just write down another structure. I know that. You might not know that yet, but there is another choice. So I'm just going to kind of do them, set them up, so that way we're ready to go. Okay, so I've just redrawn the reagent. That's it. Sulfuric acid, phosphoric acid with a little bit of heat, it eliminates. All right, so here's my first one. It eliminates. There it goes. Bye-bye. And now this carbon is going to look for its neighbors, and it's going to say, hey, you got to give me something. You know, I need this fourth bond. You're going to have to help me out here. So it looks to the one at the left, and it looks to the one at the right. These are twin brothers, right? Methyl and methyl. They're twins. Doesn't really matter which one. They both probably still live together. I don't know. But they're twins. It's going to give me the same thing no matter what. So whichever one I pick, either to the left or up above, then this is going to give me the same result. So I'm going to just target the one to the left just to make it easy. Get rid of a hydrogen that's there, and that allows you to form a double bond in between them. All right, so there's your first option. Do you see how easy that was, I hope? There's your first one. Now, we do have another option because the buddy on the right-hand side is different. So when sulfuric acid and heat comes in, there goes the OH group. It gets eliminated. And now it looks to the right-handed buddy, and it says, you know, maybe it's your turn to kind of help me out. Can you do it? And this carbon says, okay, yeah, I've got a hydrogen here. I can donate that hydrogen to make you happy, and then we'll form the double bond that's right here. Now, the question is which one of these would be preferred? And this goes back to elimination theory. The whole lecture topics in elimination is going to come back. Here we have a double bond, and here we have a double bond. How do we predict the stability of alkenes when we're looking at double bonds? Well, this is how we do it. Let's take option number 1. I see my carbon, double bond, carbon. And I'm just going to set it up like this. The left-handed carbon has a hydrogen and a hydrogen on it. The right-handed carbon has a methyl group and it has an ethyl group. All right, so there's the setup of the first one. And now let's talk about the setup of the second one. Again, I have a carbon, double bond, carbon. There's the legs. The left-handed carbon, I have a methyl group, and then I also have another methyl group on it. Okay, so methyl and methyl. The right-handed carbon, I have a hydrogen, and then I have a methyl group on it. So out of these two choices, there's one, there's two. Which one is more preferred? The rules of alkenes. Stability. The alkene is more stable if it has more groups that are attached to the sp2 carbons. Those are the carbons involved in the double bonds. In my first choice, I have 2 alkyl groups that are attached to sp2 carbons. I don't count the hydrogens. Those don't count. In the second option, I actually have 3. 3 alkyl groups attached to sp2 carbons. So with these two choices, choice number 2 is going to be a major product here. And that's because the stability of the alkene makes that happen. So we do get both choices. We do get the generation of that in our flask, in our containers, in the reactions. Yes, we do. But one is going to be more preferred over the other. And what drives that decision, number 1, is the number of alkyl groups that are attached to the sp2 carbons. Something else that I also want to say, because we're doing double bonds, we can involve stereochemistry. Oh God, stereochemistry! Yes, we can involve stereochemistry in this. It doesn't really play a factor here, and the reason is because it's not set up that way. But double bonds had stereochemistry that we labeled as E and Z, or cis and trans. Cis basically meant on the same side, trans meant opposite side. These groups are going to be much better if they are on opposite sides of the double bond. It improves the stability even more. The E and Z groups are on Z same side. Be Russian for a minute. So there's the Z. That is also the same side. So that Z is the same side, which means that E is going to be more stable. So out of these two options, folks, you're going to see E and trans being the most stable out of the orientations and out of the stereochemistry when we form the double bonds that are there. Now, number 1 and number 2 did not involve any of that. The reason is because look at the carbon to the left here. This has a hydrogen and a hydrogen. There's no way that I can rank these. I can't put one higher priority over the other. So that stops this whole easy cis and trans notation. I can't do them. If I look at number 2, this gives me a methyl group and a methyl group on the right hand or the left hand side. Again, I can't rank them. Because I can't rank them, I cannot give it an E or I cannot give it a trans notation in order to make sure that I'm drawing the most stable form. The cis and trans really are given to hydrogens. Are the hydrogens on the same side or the hydrogens on different sides? The right-handed carbon here did not have a hydrogen for me to compare. Number 2, the left-handed carbon did not have a hydrogen for me to compare. So that's what put a stop to all of that. So in this case, EZ, cis, and trans did not play a factor. I can't really do that. But I can at least determine which of the two choices are going to be the major product. So stereochemistry coming back again all over because we're involving the double bonds. I told you organic was foundational. What you learn in Chemistry 251 stays with you all the time, and it lingers in 252. So if you didn't quite get E and Z or cis and trans back in the day, folks, I'm sorry. I kind of warned you if you had me. This is stuff that will never go away. And you're seeing that here in this example. All of these little tidbits of information just drives people crazy. And that is why Chemistry 252 is a headache for some people, because they want to leave all of that 251 behind. They don't want to worry about any of it, but it wants to worry about you. It's always going to be lingering behind. You know, it's kind of like that movie It Follows. If you've ever watched that movie It Follows, no matter what you do, you cannot get rid of it. You can go places, you can get rid of it for just a few hours or a few days, but sooner or later, it's going to find you. There's no running away. It's just waiting it out. Chemistry 251, it follows. It follows you every step that you take in Chemistry 252. So that's where this video is going to stop. And the next one, we're going to continue on. We're going to look at more rearrangement elimination reactions before we finish up this section and move on to a different type of reaction.